So this is going to be a series, and we'll just get as far through this as we can, and then right at 8 we'll finish off. If you have any questions along the way, just raise your hand. We're going to start with gas appliances. Now the thing that I want to state here, because eventually this will be on YouTube, is that we are in Florida, and I mean you all know that obviously, hopefully. And in Florida we have very different types of gas appliances here than are common in other parts of the country. So 80% open combustion gas appliances are standard here. And so you're probably like, what the heck does that even mean? Because that's all we ever see here. In Florida, the air that we use for combustion, the oxygen that we use for combustion on a furnace comes in through the front of the furnace. If you've ever paid attention to a furnace, you know this has a louvered front, right? In a high efficiency furnace, the air that is used for combustion generally is brought in from the outside through a PVC pipe. So it comes in through a PVC pipe, goes out through a PVC pipe. And that seems crazy because, of course, for us, when we are sending flue gas out the structure, it's pretty high temperature still, and that's why we have to use metal flue. And that's because with these high efficiency furnaces, they squeeze so much heat out that the actual discharge is low enough temperature that you can discharge it through PVC. Those are known as high efficiency or condensing gas furnaces, condensing gas appliances. And the reason they're called condensing gas appliances is because they extract so much heat that it actually condenses water out. And that's why they have to be built completely differently, because you have to deal with that condensate. So you actually have a drain attached to your furnace in most other parts of the country nowadays. So I'm saying all this because when we're talking about the stuff we do, it's much more old school. This is the type of stuff that people were doing 20 years ago in northern climates, but here it's still standard. All right, couple tools. Now some of you are going to look at this and be like, well, I don't have any of these tools, because we have a mix of different types of folks here, but these really are the tools that are necessary to be really safe working on gas appliances. The one that a lot of you definitely aren't going to have is the combustion analyzer. Okay, so the combustion analyzer, and again, this is one of these things, we do have a couple at Kalos, and we use them for commissioning of furnaces, at least we're supposed to. We don't actually install that many furnaces anymore, so it doesn't come up as much as it used to. We're doing a lot of conversions away from furnaces to heat pumps, but you're going to see them, and so you need to know what this is all about. So we'll just go through this list quickly. Combustible gas leak detector. That is not the same thing as flue gas detection. So it has nothing to do with what's in the flue. You should not have combustible gas exiting the flue on a gas furnace or a water heater or a pool heater, right? If you actually have natural gas or propane or LP leaving the appliance, you got much bigger problems, right? It's supposed to, catch on fire before it goes out. The purpose of a combustible gas leak detector is so that you can go around and make sure that all of your connectors, everything is not leaking gas. Because in terms of the things that we're really trying to prevent here, and we're going to cover this in another slide, having unspent gas that's just leaking around a furnace or leaking around a water heater, that's among the most dangerous, because that's what we call a bomb. Combustion analyzer is there to actually test the flue gases themselves, to look at, do we have unsafe levels of carbon monoxide, do we have complete combustion going on? And that's actually a really important thing. It also can tell us things like flue draft, whether we're under negative or positive pressure in the flue. And it can tell us about our oxygen mix, all that kind of stuff. And that's a skill that you have to develop, that you have to be trained in. It isn't overly complicated. You're literally just taking a probe and you're sticking it into the flue. Biggest challenge is that manufacturers, because sometimes they're just idiots, they don't give us a place to actually test for combustion. So we actually have to make a penetration into the flue in order to measure. And that's not necessarily an easy thing to do. In PVC, it's pretty easy. You just drill a hole and you thread a plug in, right? Fairly basic. But in our market, where we're dealing with metal flue, in a lot of cases you might have B-vent, double wall B-vent, or you might have that flexi B-vent that we use in a lot of cases, which I don't love, but that's a whole other topic. You can't just drill a hole through that and just, it's not that easy to do. So you have to really think about and plan out where you're going to put holes in order to measure combustion. The other option is you can stick a combustion analyzer in the end of the flue. So for example, if you were going to test combustion on a pool heater, that's what you would do, is you would just stick the probe down into the outlet of the pool heater and you can measure it there. Now again, you wouldn't want to stick it in so far that you stick it into the inducer fan, because then you're going to tear all the blades off, which are probably all torn off anyway because they're corroded, and that's what happens in Florida. Next thing is, you're going to notice I'm talking very fast here, but we're just trying to cover a lot of the basics. The next thing is a manometer, and this is the one that absolutely every one of you should totally, absolutely, 100% have, and you should have batteries in it, and you should know how to operate it, and you should know where it is in your truck and all that stuff, because every single system we work on, whether we're measuring static pressure or we're measuring gas pressure, you need to have a manometer, and it's the same one. We call it a service manometer or a utility manometer. Not the same as the type of manometer we use for blower door testing or for the more advanced stuff. Those are precision manometers. Or the ones that we use for measuring water pressure and hydronics. Those often we call wet manometers. They're designed to measure water pressure. But for what we do, gas pressure and then static pressure, you need a manometer for that. And you need to know where all the little connectors are for gas and the tube and all that stuff. Have all that ready. I would argue that this next one is probably the most important one. And this is the one, for those of you who are in management in the room, I want to make sure that you make sure that every employee who's going to be doing any sort of service or installation on gas appliances has one of these. And that is a low-level CO detector. A lot of people call it a personal protective CO monitor or whatever. And in a lot of markets where you have a ton of gas-fired appliances, technicians should have this on them at all times. In fact, a lot of my friends will have it, they'll have it strapped on their shirt, and everywhere they go, they're just looking at what is the ambient carbon monoxide levels. Quick thing, CO and CO2, not the same thing. All right, CO2 is present in the air, it's carbon dioxide, that's what we breathe out and the plants breathe in and that whole thing. CO is carbon monoxide, and there should essentially be none of that. The only time we're going to have ambient levels of CO or carbon monoxide is if you're in a city environment where there's so many cars and so much traffic and there may be a slight low level, or if you're in a house where people smoke or something like that. But it's not safe. Any number above 0 is not good for us. It's when you get to numbers that, in the 10s, 20s, 30s, and up into the hundreds, that's when it becomes really dangerous, where you get sick and die very quickly. But it's been proven that even low levels of carbon monoxide over time can create health issues in people. And it's actually been tied to a lot of the health issues that people have. So a low-level CO detector is not something you put in anything. You don't put it in the equipment, you just have it there. But let's say you're working around a gas furnace, you're working near a water heater, and you just take a peek at it. What do I got here? You're inside a customer's house, you just take a peek at it. What do I got here? Anything above 0, you should start paying attention. Make sense? And it's not like a test. It's not like, oh, what test do I do at this low level carbon monoxide? It's just a thing that you do when you're working with gas appliances. In the home, talking to the client, when you're working around the equipment. And what we're looking for is spillage. That means where you have flue gases or something's occurring in the appliance where that flue gas is spilling and causing carbon monoxide to build up. Now, in a perfectly burning furnace, you don't have carbon monoxide at all. But almost no gas appliance that we work on burns perfectly clean. It's all about that fuel to air ratio. All right, very practical, necessary skills. Things you need to know how to do. First and foremost, you need to know how to carry out a thorough visual inspection. You need to know how to look through the equipment and identify things that are a problem. Let's do some quick obvious ones. Anybody have any obvious things that would be a problem if you're looking at a gas-fired appliance? Talking about water heaters, gas furnaces, pool heaters.
It's not connected. Gas line's not connected.
Gas line's not connected. Yeah, that'd be obvious. Yeah, that would be a big one. Now, that kind of sounds like a joke, but I want to give you a really good example. I went to a property management house where somebody else converted, it's always somebody else, never us, somebody else. Somebody else converted a gas furnace to a heat pump. So they removed the gas furnace, they put a heat pump in, the water heater was still there. So the water heater still had gas, there was still gas to the house, probably in the stove and other things, right? And what did they do when they disconnected the gas line?
Turn it off.
You just turn it off, right? That's obvious, right? Okay, so they just turned it off. And then what did they do to cap the gas line? Nothing. Okay, this is a vacation rental house with now a pretty red handle that's just turned sideways in a converted game room. So who goes into the converted game room? Kids, they see that pretty red handle. Hey, what's this do? I mean, you know what would happen if that had happened? We're talking about like in terms of the risk level. So you bring up something that's kind of like, is it connected? It's sort of a joke almost, but gas lines that are not in use or taps on gas lines, they need to be capped permanently. Okay, you need to pay attention to that. So that's a really good example. Leaking gas lines, I mean, it's a serious problem. Something that a lot of people don't realize is that gas, natural gas and LP, they don't have an odor to them naturally. That smell that you smell in gas, those are mercaptans that are added to the gas so that way you can smell it, so that you can tell. And with a big gas leak, you're gonna know. But the problem is a lot of these houses that we work in go unoccupied for long periods of time. So you could have a bomb that's just building up and then eventually causes a major problem. What are some other things in visual inspection?
Rust in the heat exchanger.
Corrosion? Yeah, corrosion is huge. Gas pool heaters, I mean, it's a massive thing because you have this chlorine environment. Now, one thing that I will say that I didn't know, even when I started working on gas pool heaters, this is just a complete aside. When you see gas pool heaters that corrode out really quickly, a lot of times it's because we're flowing too much water through them and it's causing them to condensate. And that condensation is actually what's causing them to corrode out on the inside, just fun fact. We have to pay closer attention to water flow rates and the actual, installation instructions. Those are always really handy because it has all that information in there on how we install them to prevent some of these problems. But even in a perfect world, these things just fall apart on you. So if you go up to a gas pool heater and you see the burner trays laying sideways and everything's all corroded out, what should we do with that gas pool heater?
Turn it off.
We should shut it off and say it's unsafe and quote them a new gas pool heater. Now, if they go back and they turn it back on, that's on them at that point. But if we shut it off, we document it, we tell them that it's unsafe, then we've done our job. And we do not do that as much as we should. I'm specifically mentioning gas pool heaters because that's really the only ones that we see this a lot in Florida. In Florida, our furnaces run so rarely that you're rarely going to run into a situation that you find a rusted out cabinet or a rusted out burner assembly on a regular furnace. But if you did, then that would also be something to pay attention to. What are some other things in a visual inspection? I'll give you some more. So alignment of the burners. So a lot of cases when you install a furnace, something gets a little tweak sideways, and when you go and run that furnace, which by the way, we need to, every time we do a maintenance on a gas appliance, every time we install a gas appliance, I mean, I know it sounds obvious, the people who are in other markets are gonna laugh, like, why on earth would you do it? But because we just don't think about heat a lot. We just don't have it in our head. We need to make sure the gas valve is on, we need to make sure the gas supply is on, we need to make sure that we don't have leaks, but then we need to run that furnace and look at the flames and make sure that everything is aligned properly. In a lot of cases, you get a burner that's kind of off and now all of a sudden that flame is impinging, which means the flame's hitting metal. That flame hits metal long enough, stuff's either gonna melt or get damaged, it's a problem. And then you're gonna have safety issues. What else? Another one is when you run a gas furnace, especially in our market, because we have these 80% furnaces, and in 80% furnace, you have the burner assembly up top, right? And you can watch the flames, and then down below, you have the cover and the blower and all that. That should be covered whenever you operate. That's another thing, they don't work right because then, you have this air sucking in. You have to have that covered, and you should watch the flame when it first starts up. When it first starts up, the flame goes first, and then the blower starts. If the flame goes first, the blower starts, and all of a sudden the flame starts changing on you, that's an indication that you're mixing the air side, the blower side, with the air that's entering the furnace for combustion. So that's another really big factor. Another huge visual inspection area, you notice I'm focusing a lot on this, but these are the things that you really have to do. Another huge visual inspection area is where is this appliance getting its air from? It's called combustion air. That's a fancy word that just means where's the thing getting its oxygen from? So if you have a gas furnace or a water heater slammed into a closet with a door without louvers, that's a problem because it's going to work fine when the door's open and you're working on it, and then you shut that door. Now where's it going to get its air from? Well, cracks, crannies, wherever it can, but that can create a really unsafe condition. Just think about it. What do we need for combustion? And I guess I should probably jump forward so that we can, what do we need for combustion?
Air, fuel, and heat.
Air, fuel, and heat, right? So if you have the fuel and you have the heat, but you don't have the air, specifically the oxygen in the air.
It's the fire triangle.
Exactly. Well, what do you have? You have a really unsafe burning condition, and that's when you get incomplete combustion, that's when you can get flame rollout, that's when you get excessive carbon monoxide. All of these really bad things we don't want occur because you don't have enough oxygen. So every time we're working on any gas-fired appliance, we should be paying attention to where's the oxygen coming from. Now, there's calculations that you do about confined and unconfined. This is not a class about design. This is a class about practical things that technicians need to be paying attention to. And whenever you walk up to a gas appliance, you need to be thinking about this fuel-air mixture. Go ahead.
I've also ran across it where a natural gas furnace is installed, and it's actually a propane house,
There you go.
and you make sure that...
That happens a lot. And in our market, anytime you notice that it is a propane house or LP house, stop and make sure that everything's been converted. Because very often that's not the case. Now again, that's rare. In most cases, if it is an LP house, you're usually not going to have a gas furnace in Florida, but you could, or you could have other gas appliances. You know, gas tankless water heaters or gas pool heaters are a real common one. And I'm in my house, we're putting in a pool and for the hot tub, we've got an LP pool heater, and it's very easy to order the wrong one or fail to convert it. So these are all things that you need to be paying attention to. Another one is gas piping. This is especially true with pool heaters. In this market, people will use appliance gas connectors to connect everything. These little tiny, you know, half-inch, three-quarter inch appliance flexi gas connectors. They're yellow and those aren't for connecting big stuff. Those are for connecting real small stuff that needs to be able to be moved around. And if you put the wrong size gas piping on an appliance, you're going to have the opposite side where you don't have enough gas pressure, and now you can have flame rollout, all kinds of other problems, flame impingement, all kinds of issues. This is especially true on pool heaters. Out of curiosity, anybody know what the biggest BTU furnace we pretty much ever put in Florida is?
90 BTU?
It's about 130,000 BTUs, about the biggest you're ever going to see in this market, right around there, right? What's the smallest pool heater BTU that we put in? Anybody know? 250,000 BTUs, which means that these little tiny pool heaters are moving twice the BTUs, which means in order to get more BTUs out, what do you got to put more of in? Gas, right? And it's proportional, right? So you need to put twice as much gas in to get the amount of BTUs out. It's a pretty simple equation there. So you should have big piping going to pool heaters, especially when you see a 400,000 BTU gas heater. I mean, I know there's people who are going to watch this later and laugh at me because of how dumb the things I'm saying are. But these are the sorts of things you have to really pay attention to. You know, in the words of Vanilla Ice, you have to stop, collaborate, and listen. Next thing is use a manometer to set the gas pressure. Every time we're setting up an appliance, we need to be measuring gas pressure, okay? If we're not doing that, then just pretend like you are, and next time make sure that you do it. And if you don't know how to do it, make sure that you learn how to do it. We have really good 3D videos on all this. It's not that hard. We'll cover that in this series as well. But make sure to set gas pressure. Now, some people will say, well, should you be doing that on every single service call? My assertion is that if you set it initially, then you probably don't need to do it on every service call. On a maintenance, it does make sense. But again, it's one of these things you want to document what the set gas pressure is. You really should be doing that with a combustion analyzer, which is why I'm a fan of doing it initially, and then just doing a solid visual inspection using, you know, your other devices. Again, this is a Florida thing. In other markets, they're like, that's heresy. You should be checking gas pressure every time. In our market, it's just so rare. The next thing is using that personal CO2 monitor to measure ambient CO. That's that little one that you keep on you, but there's also something called a low-level installed or permanent CO monitor that we should be suggesting to all of our clients who have gas appliances. Okay, I've said this like a zillion, billion, trillion times, but in residential it just gets missed because, again, and I've said this a lot too, we just don't have as many of these here, so it gets out of our consciousness. But the CO2 or the CO monitors that are inside the house that alarm and are required by law, the UL listed ones, they don't start alerting till like, I think it's 100 or 200 parts per million. So you could have a very dangerous ongoing operational condition that could be making people sick that the alarm's not going off. And that's where a low-level carbon monoxide monitor is a really nice thing to have. You put it, you know, if it's got an attached garage, you put it outside the garage, you put it near the kitchen. Again, especially for people who have like a gas range and all this, there's all this stuff going on in the politics right now about the safety of gas ranges, and it becomes like this right-left issue and, oh, you know, whatever. Look, I'm not an advocate of taking away people's appliances, but I absolutely know that this is one of these things that older generations understood better, and nowadays we have people putting in gas ranges in cases where you don't even have a hood over top of it that vents outside. I stayed in a vacation home in Tennessee, this big old Viking range. You know, somebody was really proud of what they put in. It's got all these burners, and up above it is a range that doesn't even vent. I mean, can you imagine the CO that had to be, and of course I didn't have my personal monitor like my northern friends, so I couldn't tell, but can you imagine if we were cooking a big meal with my kids and what the CO levels would be? So it's just one of these really silly things. The take that people will have is, we've been doing this for years. It's like, yeah, but we also used to, like, you know, drink uranium energy drinks, and people's teeth used to fall out. You know, you used to have cocaine and Coca-Cola. Like, there's lots of things we used to do that were bad for us that we should not do anymore, and this is one of them. And it's not to say that gas appliances are evil. I'm a big fan of gas, but you have to think it through, and we're especially at risk when we're just going along happy-go-lucky and not paying attention to this stuff. So that's where a low-level CO monitor, suggesting that to the client. And in fact, I want us installing them every time, just as part of the install. Just installing a low level, because what does that do? It's cheap insurance. These things are battery powered. You don't have to, the batteries last for like 5 years or whatever, or 3 years, whatever it is. And you just put it on the wall, and even if you get up to 3 ppm and your CO, it's going to start alerting, and it's going to let people know there's a problem. And that protects us from having somebody die on our watch, and it protects them from dying, which is a really good thing for most people. The final thing is that combustible gas leak detector, that final step. Now, old timers will tell you, hey, just take your lighter out and just run it underneath whenever you see a flame. That's not, you know, it's not a great idea. It's not the best idea. If any of you have ever had your eyebrows melted off when you're trying to light a grill, it's kind of like that. You know, it's not the best idea. My wife still makes me light the grill to this day because of an incident that occurred with her eyebrows. Anyway, this is where we'll finish for today. Gas furnace sequence of operation. This is the sort of thing you should know like the back of your hand. It's really, really important to know, because then you can notice things that are outside of the normal. All of this presentation, if you guys want it, I'll give you the whole thing in a PDF. You can keep it in your truck and paper if you're that kind of thing. But all this stuff is also available on the HVAC School app and hvacrschool.com. Those of you who don't use that, just start using it. Like, you just go into the search bar and just search gas furnace sequence of operation, and you'll get a podcast and a video and 1,500 tech tips, and you'll get so bored of my face if you're not already. So step one in gas furnace sequence of operation is you get a W call. W is white. That's your heating call. And you'll notice this still, like, you'll still see some thermostats that allow you to select, is it a furnace, is it electric heat? And that's one of the really big distinctions between those two things is, do you call for the blower right away? So you're going to notice this. You don't get a G call traditionally when you have a call for heat in a gas furnace. And the reason is because you want everything to heat up, and you want it to create a draft before that blower comes on and cools everything down again. Right? You don't want a cold draft in the house, and you also want that flue to heat up in traditional furnaces, so that way it drafts better, and when that air first blows out, it blows out warm right away. So that's why you don't have that blower come on right away. Does that make sense? Like on a heat pump, G calls, G is your blower, and W is your heat if it was electric heat, or, you know, Y, and then you have the O, obviously. You don't have a call on O in a typical heat pump, but I digress. In a gas furnace, generally, when you go into heat, it's just a W call. W calls, next thing happens, the board confirms that the pressure switch is open to start with. This is really key, because this will happen sometimes. Your actual flue pressure switch, your inducer pressure switch, whatever you want to call it, the pressure switch that confirms that you have an operational inducer fan, it has to start open, and then it goes closed. If for some reason that switch is closed to begin with, then the board's going to fault out and say, no bueno, that inducer fan was not on, it should not have been closed yet. Does that make sense? That's what the board's looking for there. Then your inducer fan starts. One quick, very important fact, if you get a little deeper into this, what do you think the pressure is in the flue pipe once the inducer fan starts? Do you think it's positive pressure or negative pressure?
Positive.
You would imagine it would be positive. So you imagine, we all imagine, that that inducer fan is blowing the flue gases out of the flue pipe, right? It's actually not. It's just providing air for combustion. So it's bringing air in, but once that flame gets started, you actually have negative pressure at the outlet of the furnace. And the reason is because you're basically creating this vacuum cleaner, because what does hot air do? Hot air rises. Hot air is buoyant. It floats in colder air, right? So for those, again, we're in Florida, so those of you who are born and raised here, you don't have to think about any of this. But if you ever had to start a fireplace, you know how tricky that can be. You got to get that draft going, right? And so it's that heat that's going up the chimney that then draws the air in, and it just kind of keeps the thing going. It starts off and it wants to come out back at you, right? Same principle here. So what happens is that flame starts, heats everything up, and then that inducer goes, and now you have this hot air rising, which acts like a vacuum at the bottom, right? So because you have this stack effect, it's actually creating a negative pressure at the bottom and drawing everything up. And all that inducer fan is doing, that's why they don't call it a power venter. There is such a thing as a power vented furnace, but these aren't power vented. These are just induced draft. You're just inducing air, and the only reason you have to have induced draft is because our heat exchangers are complicated nowadays. Back in the day, if you go to an old natural draft furnace, go in there, you'll just see these flames that are just upright. They don't have these gun burners that shoot out at you. The flames just kind of do this, right? Like looking at a grill or something. And there's no power venting. There's no induced draft. All it does is you just have these very simple heat exchangers that do this, and the heat rising is what actually brings it out. It's like a water heater, same way a water heater works. You don't have that. The reason why we have it nowadays is because we have these heat exchangers that are much more complicated, either tubes or they're like built into plates. And so because of that, we have to bring some air in to that furnace. So back to sequence of operation, W call, make sure that it's open, then inducer fan starts, then the board says, now this pressure switch better close, right? And it's a negative pressure switch for the stuff we work on. So it's looking for this negative pressure. If it doesn't close, okay, because this is going to happen a lot when you work on gas appliances, that switch doesn't close, it's not a bad switch. Okay, sometimes it's a bad switch, but it's almost never a bad switch. Why isn't it closing? Because there's not the pressure that it's looking for, right? How could you confirm? Well, you could use a manometer, but generally you're going to start doing a visual inspection. Did a bird build a nest in the flue, right? Did the thing somehow get full of water because of condensation or because the cap fell off and water ran down in? You'll find cases where the tube is bent or kinked or damaged or broken or has something blocking it. There's all these things that happen. It's almost never the switch. Again, it's sometimes the switch, but you don't start with the switch. It's just like saying, I think it has a bad compressor. Okay, you end there, but you do everything else before you get there. It also makes sure the board simultaneously confirms that the safety circuit is closed. That's kind of out of order. I mean, it's just in there. The whole time safety circuit needs to be closed, and that's basically just daisy chained. It's just in series. Any of those safeties open, it's going to cut the thing off. Ignition sequence begins. This is just showing a hot surface igniter, but it could just as easily be spark ignition. And so that thing's going to glow. It's going to heat up. Then the gas valve opens, and that's on a timer. That timer in modern furnaces and gas appliances usually is flexible, meaning that the board is actually looking at how long it had to heat up last time, and it keeps shortening the time a little bit until it doesn't work, and then it goes to that last timing. And the reason that is because the longer an igniter stays heated up, the longer that it's applying power to the igniter, the more likely that igniter is going to fail, or the reduced life of that igniter. So a lot of manufacturers, because people will say this, will say, well, it's a 5-second heat up time or 10-second heat up time or whatever. That isn't consistent. That board's going to try, on a lot of the modern furnaces, it's going to try different timings in order to keep that igniter energized for the lowest possible amount of time. Go ahead.
On the topic of the igniters, watch, I think it's Linux, has like a 90-volt igniter. So you got to keep an eye on that and see what voltage you're supposed to be getting.
Correct. You don't. Also, there was older igniters that Trane used to have where they actually used like a chopped sine wave, so you couldn't even measure, kind of like you have with a modern dimmer switch. You couldn't even measure it with a voltmeter. So there is some complexity there. There's two different common types of igniters. The old ones are silicon carbide. The new ones are silicon nitride. As far as you're concerned, the only difference is they look a lot different. The old school ones look like this, like an old oven coil. The newer ones are just like a little stick or just like a little round rod. Then the gas valve opens once the timing, and then it's actually going to dump gas over that igniter. Then it proves flame, and this is where I really want to end here, because this is the part that just blows everybody's mind. Okay, in order for a furnace, this is where it goes wrong a lot. In order for a furnace or a pool heater or whatever to prove flame, it has to be well grounded. You have a flame rod, mostly. Sometimes it uses the igniter or some other strategies, but you generally have a flame rod. And that flame rod needs to be immersed in flame in order to connect basically from the board through to ground, and it can prove a current. And that current is a DC current, and that's why they call it flame rectification, okay, to get real fancy. It doesn't matter. The point is, in order for this whole thing to work, that rod needs to be immersed in flame. So it needs to be positioned correctly. It needs to not be broken. The ceramic shouldn't be broken, any of that stuff. It needs to be clean. So not covered in carbon, and the furnace needs to be well grounded. So when you run into gas pool heaters, for example, and all of a sudden it's going through this whole sequence, it's trying to prove flame. You see flame, but then it shuts off again. So it goes through all this and then it shuts off again. That's almost always because of an issue with this flame proving, and a lot of times it's because of grounding. And a lot of times it's because of grounding, because the whole thing is a corroded mess and nothing's grounded the way it's supposed to be anymore. And when everything is a corroded mess, what do? We shut it off, we tell the client that it's unsafe, and we quote them a new pool heater. And then they scream and yell and tell us that it's been working this way forever, and how come we didn't tell them before, and all that stuff. But you know what's a lot better than, flip it. It's annoying when clients complain. It's a lot worse when it explodes in the side of their house and creates a big fire, right? So that's a lot worse, so we want to be pretty conscientious about that. Now, I'm not saying a little bit of corrosion here and there. I'm saying the reason why it's not grounded is because now that entire burner assembly is no longer in place. In order for things to be grounded, they have to be attached mechanically, metal to metal. And when that metal is now rust, it's very difficult for that to happen. But the same thing is true in gas furnaces. You got to make sure that they're grounded properly. We'll cover specifically how to do that electrically, how to test that in future classes. But a lot of this is just visual. It's just obvious, right? Do I have a well-connected ground? Go back to where it's connected to the panel. Is it connected properly there, right? That's the obvious first steps. We become masters of the obvious before we start overthinking things. Most of what you're doing here is just paying attention to things that you could catch yourself if you were just looking and paying close attention. Final thing is blower starts. When that blower starts, again, panels on the blower section, watch that flame. Get in the habit of doing that on every maintenance, every system you install. Because if you ever watch a flame, blower starts and the flame starts doing this on you, orange flame, all that kind of stuff. Now, a tiny, tiny bit you may get just because there are tiny little gaps and cracks just in the cabinet, especially when you had the panels off, whatever. So a little tiny, tiny bit, but it should stabilize very quickly. If it's nice and stable, blower goes on and it really starts moving on you, that's an indication that you have leakage in between those two air streams. Your combustion air, which is for the burner, and your blower, which is down below. So one final thing I want to mention, and again, we'll talk about this in the next session. So this class is going to get broken up multiple ways. This is basically preparing for heating season gas, part 1. Look for any signs of heat damage. So if you're working on a gas furnace and you're in a garage or you're in a closet or you're in a mechanical room, look for the water heater as well. Look up at the top of the water heater on that draft hood. Okay, that's the little part where it attaches to the flue. And that top right underneath there. If you see signs of like melting and burning and scorching and like water damage and stuff right there, it's a problem. You don't need to, I don't even care right now if you know how to fix it or not, but you need to stop the presses and then talk to somebody who understands gas, because we need to get that fixed. It's very dangerous for our clients. And a lot of the times in our market, carbon monoxide issues are not necessarily from the gas furnace, because our gas furnaces run so infrequently. They're more often from the water heaters. water heaters being installed improperly, the flues being installed improperly, and then negative pressure in the space, depressurization of the space that then causes that water heater to backdraft. Same thing is true in the burner assembly. Just take a look down at the bottom. If you see any signs of like things having melted or anything that looks abnormal, we know how water heaters should look, right? The paint should be in decent shape, all that kind of stuff. If you see scorching or signs of moisture damage, tell somebody about it. And hey, that's a great opportunity for us to put in a heat pump water heater, which will work a lot better for them anyway in our market. So these are things where being attentive and actually serving the client, thinking about their safety, can actually lead to sales for Kalos, right? In a positive way, like, hey, this is an opportunity to now upgrade because what you've got here is unsafe. Make sense? Any final questions? I went over and I swore I would not. Cool, that's part one. Thanks, guys. Appreciate it.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. Also, don't miss out on our free mobile applications available for both iPhone and Android. They're packed with handy tools and calculators to make your job even easier. And while you're at it, join our thriving Facebook group. We're all about community. For techs, by techs.